By a raise of hands, I'll be happy to know how many developers are there actually. Like, okay, so all of you, that's good. How many of you ever developed, or sorry, how many of you have Rust experience? That's a good ratio. How many of you ever developed smart contracts in general? And in Cosmos? Okay, that's still good. And have any of you ever developed or tried to develop something with secret? Smart contracts with secret. Okay, fair enough. Okay, that's perfect. Yeah, so let's begin. Secret network, our vision is to create a world with blockchain where we also we still hold all the important principles for blockchain, the trustlessness, the correctness, the decentralization. But we also believe that our vision, we can't imagine blockchain get real world traction, real world adoption without privacy. If you think like any real world application has we have to store some things always, like some things sensitive, like medical information, passwords. Maybe want to monetize content, like we're going to talk about here today. So we believe that privacy is very important for people, and that all public by default that we have today is, we believe, not good enough. And we want to bring the privacy vision not only to secret, but to other chains as well. We create this privacy vision with something we call secret contracts. So most of you are familiar with smart contracts, and most of you even developed smart contracts in Cosmos. That means you are familiar with CosmWasm, which is the smart contract engine, the most popular one on Cosmos. We took that, we actually helped develop it for a while. I think we were one of the first chains to ever deploy it. And we altered it a little bit. And we created something we call secret contracts. And the difference between secret contracts and regular smart contracts is that all the inputs, all the outputs, and the state of the contract is private. It's encrypted. The way we do that is we use a technology called secure enclaves, or TEEs, which stands for Trusted Execution Environment. And with a combination of pretty basic cryptography and key management, we basically created a system where users were like the data sits encrypted in the storage, and only the user can access his private data, and he can share it with whomever he wants. And it's like we created a very flexible system. You can share it with whomever you want. Contracts can interact with each other, and everything stays encrypted, and not even the node runners can access the private parts of the data. The chain is public by default, like our native token is public. Everything's like vanilla Cosmos SDK. When you interact with secret contracts, that's where the privacy kicks in. Yeah, we based on Rust CosmWasm v1. You'll see in a bit when we'll start to look at actual code that is very similar to vanilla CosmWasm It's not going to be very different. Yeah, any questions? Great. I will also share the link to the presentation later, and you will be able to go to links and stuff. That's good. So a little bit about this privacy vision. I will give some basic use cases just to open your mind and just give you a sense of what can be built on Secret. So first of all, and one of the most important building blocks we've created is something we call okay, never mind, I'll get to it later, but private transfer of tokens, okay, or private swaps. So when we talk about tokens, I think it's pretty obvious that privacy is very, very valuable, because the balances of the balances of the users is hidden, is private. They can share it with whoever. The transfers are private as well, so no one can actually see the transfer history or stuff like that besides the user. So it's something like Zcash or Monero, but it's composable. We can create. We don't do only private transaction. We can create a whole ecosystem around it. We can create an AMM, a swap mechanism, and all of that really benefits from the privacy by default. We also able to create on-chain true decentralized randomness. This is huge. Any randomness that exists in blockchain today is always off-chain, is somewhat centralized or dependent on off-chain services. Why is that? Because privacy, randomness is like in computer science, computers in general, it's not really random. Like, right? We call it pseudo-random, because all randomness in computers are based on a seed. We start the randomness with a seed, and then every random number that comes, like get generated after that, is kind of expected if you know the seed. So if I know the seed, I will always know what the next number is going to be. If I'm creating an app that is dependent on randomness, I cannot store the random seed on chain because it's public. That's why we have oracles. That's why we have stuff like Chainlink, VRFs, because we can store this data on chain. Well, now we can, because the state of secret contracts is encrypted. We can store the privacy seed on chain. We can roll it with time. We can change it. We can create, we basically create an on-chain randomness which is fast, more efficient, and cheaper. And again, it's very flexible, very composable. You can, it creates a lot of very interesting use cases. For example, stuff like on-chain gaming. So if you ever tried or have any experience with playing stuff like casinos or games on blockchain in general, most of them depend on randomness. But for all we know, we don't know if it's if we can trust this randomness, right? So with Secret, we can create fully on-chain decentralized games. For example, if we do blackjack, we can create everything on chain, right? The deck can sit randomized on chain. Nothing is dependent on any off-chain services. We have stuff like tower defense on the right, and we have Bushi, which is actually a very cool game that they both should go on mainnet very soon. And besides randomness, we also have private game state, right? Because every most basic PvP or PvE games have some kind of private game state for, I don't know, holding items, stuff like that. So this is very valuable for gaming as well. We see use cases like secret KYC or credit score, which is pretty obvious why we need privacy around that. We don't want to share all our credit history or credit score with other people. We don't want to be exposed like that. Secret KYC actually is a very interesting use case because in traditional KYC, like we know today, all our, and we're talking about super sensitive data, like our identity, where we live, what passport do we have. They all stored in when we do KYC, they're all stored in a storage somewhere. We don't really know like how it's protected, who's protecting it, how many times it's duplicated between different databases. And with this, we can create a system where all that data sits encrypted on-chain, decentralized. No one really owns the data. So it's much more secure. Yeah, so that's pretty cool. That's something I'm personally very excited about. And we actually have a team that's called Secret Sibyl that's creating a credit score for Web3. If you want to check it out, that's pretty cool. Another use case we can create is trustless on-chain wallets. So again, if we have encrypted state, we can save passwords on-chain. We can save private keys. We can do multi-party or threshold wallets, where one party is the actual user and one party is the chain itself. We don't need to trust third-party service provider anymore. We don't need to rely on him to be online. The chain is always online. It's always available. So that's amazing. You can create like arbitrary access control rules. For example, you can decide you don't want this or a specific wallet to spend more than $1,000 a day, and then you can actually protect yourself against hacks or stuff like that. So talking about building blocks, one of the most important building blocks, as I mentioned earlier, is actually the transactional privacy, the private tokens we can create on Secret. We call them SNP20s. They are very similar to CW20s or ERC20s that you're probably familiar with. It's basically the same spec, but with a couple of additional features to ensure privacy and privacy-enabling tokens. And we see very heavy, like this standard is very heavily used across Secret Network in all DeFi, basically, which again creates a very unique and very interesting like a DeFi ecosystem where everything is private. Everything is front-running resistant, actually, because everything sits encrypted in the mempool. So front-running becomes like not what's the word? Not possible. Thank you. Because everything's encrypted. So that's pretty cool. We also have SNP21s, which are basically NFTs. And the cool thing about secret NFTs is, again, the metadata is private. We don't have right-click save anymore. We can have actual private data in an NFT, which no one can see except the owner. And the owner can decide to share it, to put it in a gallery, to share his keys or his password with the world. He can do that, or he can decide to keep it to himself, right? And that really takes NFTs beyond the like, you know, the digital arts, the JPEGs, the monkey pictures, which are cool. Don't get me wrong. I really like the NFT the NFT space. But now we can create like things that are actually valuable. We can monetize content. We can save like personal private data on an NFT, and we can actually like. I personally feel, and we feel at Secret, that private NFTs can actually actually implement the vision of NFTs. And the streaming service that we are going to design and build today is based on NFTs. So we're going to talk about it later in a bit. Yeah. Yes. I mean, it really depends on the use case. So it's very flexible. You can build it however you like. So by default, the SNP 721 spec, you have your public metadata and your private metadata. It's split into two. And then you can choose if you want to keep part of it private, public, but you can definitely change. You can implement it however you want, and it's very flexible. Any other questions, by the way? Feel free to stop me if you have any questions. So a little bit about access control, and I've talked about like users having the ability to having the option to share or not to share. So we've come up with two ways to allow users to access their own data and to share it with other people. The first one, and the first one we introduced is called, we call it a viewing key. It's basically a password. So we create, so most of you come from like know smart contracts development. And we basically do we implement queries. So for example, if we have a token or a SNP20, we have a query of the balance, right? I want to query my balance. One of the the query is implemented in a way that first of all it checks. I need to provide my viewing key. The viewing key is stored on chain. So if I decide my viewing key is 1, 2, 3, 4, I query my balance with this viewing key, this password, so to say, so to speak, and the secret contract checks that the viewing key checks out, and then he returns the output to me, like to the querier, and the output is encrypted, of course, and like only the sender of the query can open the data. The problem with viewing key, or like the inconvenience with the viewing keys, is that we have to store the viewing key first, right? Like the user has to choose his password before he actually can use it. So it's an extra transaction we need to make. Like if we if someone sends us to or we send to a new address some tokens, first to view my balance I need to create my viewing key, I need to send a transaction, and only then I can query my balance with this viewing key. Otherwise I won't be able to have access to this data. And then we introduced permits. So the cool thing about permit is that what we actually do is the user signs, it's very simple actually, the user signs a message that's basically saying, hey, I'm the owner of this address, please show me my balance. And I sign this message with my private key, with my address, like the private key that attached to my address, and the contract can verify this. The contract can verify this signature and make sure it's actually the user. Then I can share this permit with other people and by that we actually we don't have this first transaction we need to send. So that's cool. Any questions about it? Yeah. The viewing key is signing? No, the viewing key is basically just a password. So you need to set it first, then you save it on in the state of the contract, and then every query you do subsequently you have to provide the password with your query, and then the contract that just checks that this is the same password and gives you the result. Is that answers your question? Yeah, okay. Any more? Cool. So let's talk a bit about what we're trying to build here today. We are trying to build a decentralized streaming service, something like a Netflix, some way to monetize video content and distribute it to users. So on a very high level, and if you guys ever worked at something like streaming or DRMs and you have any past experience, I'm way oversimplifying it, so I apologize in advance. But basically how it works today is that services like Netflix, like HBO, like Disney, they have something called a DRM. DRM it stands for Digital Rights Management, and it basically defines the scheme with which the actual video content is protected. So this picture on the right, I just took it from somewhere. It's not really important, like the actual steps and the flow. What is important to understand is that first of all the video content is stored on company-owned servers, right? The company itself, the streaming service, owns the rights to this content, and they store it in their own servers. They store it encrypted. Obviously, users don't hold the keys because users don't own this content. Users are heavily dependent on the streaming server, right? Or the streaming service to be online. If it's not online, we can't access the content. If a local server, they basically have for each country they support, they have local servers that we can interact with to create a faster connection, bigger bandwidth. So if my local server is offline, I will not be able to watch my movie with good quality, at least. So that sucks. And the thing I marked with a red thing there is actually shows the encryption of the video content is obviously encrypted in the servers, and what they do is they re-encrypt the videos all the time. So they switch keys all the time to make sure the keys don't leak or anything, and they really do everything they can to ensure that the user or the people that actually watch the content have to be subscribed, right? The moment you unsubscribe, you lose access to this, which is fine. But on blockchain, we can't do this, right? In blockchain, we don't want, or in Web3, we don't want to store the video content on servers, on centralized servers somewhere. We don't want to rely them to be online. We don't want to rely on a specific company or a specific streaming service to have this content online all the time. It's kind of beats the purpose of what we do here, right? So decentralized streaming service will look a bit different than what we are used to in Web 2. Obviously, it's like a very simple and like probably oversimplified like design or implementation, and it can be very much improved. And this is only one design choice. But what we thought of is, as I said earlier, base this streaming service on NFTs. So we want the video content itself encrypted and be stored on-chain to be always online, always accessible. We want the users to like have the ability to prove they own a certain video or like supposed to have access to it. So what we are going to do is to store all of we're going to encrypt our videos off-chain, offline. Then we're going to upload them to IPFS. They will be stored on IPFS encrypted. And then the NFT that we are going to give users actually contains the decryption keys for that video. And that creates a service that is not platform dependent. We don't rely on anyone except for the blockchain to be always available, which is good. And we're going to create a service which is not subscription based, but it's like a per video model. So if I want to see a specific video, I will have to pay for it. Then I will receive my NFT, and it will be available for me always from now on. The reason we do this is because the streaming services, they re-encrypt their video content all the time. We can do that because once we upload encrypted video on chain, it's always there, right? That's one of the good things about blockchains. It won't go away. So once you give someone the decryption keys, it's game over. Like we can't do a subscription-based service when we give users the keys and then re-encrypt it and re-upload it to the blockchain, because the old videos with the old decryption keys will always be there, right? So we changed the model a little bit, as I said. The purchases will be on a per video basis, and once a user has this video, he has it forever. No, like the service can't just decide that it takes down your favorite TV show or something. You'll always have it. You always have the decryption keys and can always access it. Any questions at this point? Right. That's a good question. That's an excellent question. So first of all, I'll say that the problem with piracy, let's call it that, is it's there with Web 2 as well. Because when I view it's very, I can just copy or record the screen very easily and just distribute it illegally. So we still have kind of the same problems. Now, as for hiding the actual decryption keys from the user, it's a problem because who does have an access to this key with this model? Some kind of centralized party, right? Like the idea is not to not be dependent on a specific party. We want the users to have control. So yeah, I agree it's not perfect. I agree that once the user has the decryption keys, they can do whatever they want with it. But first of all, like, it's not a super trivial thing to download an encrypted movie, which we split up to chunks, and like it's in a weird format, and you don't really know how to decrypt it. That's not a good answer, obviously, but yeah, it's not perfect yet, but it's a very simple implementation just to showcase the ability of like, you know, monetizing and distribute content. It can be improved for sure. Right. Okay. Okay. I see what you mean. So you're saying let's not show the user the decryption keys. Let's offload it to the contract. The contract can say, yeah, that's a great way to implement this. It's get a little bit more complicated because videos or video files are very, very large, and it's not super trivial to store it on chain, on a regular chain, right, or on a general purpose. So you need to have some kind of custom chain to allow something like that. So if you're creating a custom chain specifically for a streaming service, for sure, yeah, maybe like it's probably possible, and it will be way better. That's one of the ways to like implement it for a real world use case. When we upload it to a different chain, and we have only the decryption keys on our chain, it makes it more difficult because, but if we have some kind of Cosmos IPFS and we have IBC, that makes it a lot easier. So that's an idea. So yeah, it for sure can be improved, and that's a very good point that you're raising. Any other questions? Cool. So a little bit more specifically, and I'm sorry, you can obviously see that as we go further down the presentation, and this is actually like my slides, that the quality is degrading, so I apologize. So we have two, like in the app that we're going to build, we have two very basic flows. Can you see it clearly? The text? Okay. So we have a contract that is called, like the only contract that we actually need to build here is the access manager. And the access manager will be the contract that will manage the access to the videos. It will going to collect the payment from the users. It's going to mint the NFTs for the users. And the content creators that wants to upload their encrypted content will list their videos with this contract. So this contract will hold the catalog of all the videos that exists in this service with this implementation. So the first flow is for the content creator that wants to list his video. He first needs it's not written, not showing in the flowchart, but he needs to first encrypt his video and upload it to IPFS or some kind of decentralized storage. Then the user just called, or the content creator called the new video function in the access manager contract, and basically list the video. He need to, we'll see it later, but he needs to specify basic stuff like the name, the description, the URLs for the encrypted data, and yeah, all the basic stuff you can imagine. The second flow is when an actual user wants to purchase a video and watch it. So first of all, he needs to interact with the access manager. He needs to send some funds in order to purchase a video. And then the access manager calls pre-deployed SNP 721 or an NFT contract. And then the contract himself mints an NFT for the user. then the user holds this NFT, he holds the decryption keys, and by this point, we can create a front end or a UI that handles all the like the access to the video from the decentralized storage, and all the decryptions are handled in the front end. The model of this implementation is that when we upload a new video in the first flowchart, the access manager actually deploys a new SNP 721 for each video that exists. Okay, so each video that exists on the platform has its own SNP 721, and every user that purchases it, like the access manager mints a new token of type of this SNP 721. Was that clear? Any questions at this point? Cool. Yeah. So let's do maybe a 5-minute break, just to refresh a little bit. And then we will continue, and we will look at the actual code of the contract, and we will go over it. Let's get back at 5 minutes to 11, like 10:55. Is that okay? Oh, so if we actually send some instructions. So. I will go over most of it myself, so you don't really have to download anything. But if you want to follow along and maybe at the end experiment a little bit and like look at the code yourself, you can clone this repo. It's public, Secret Labs /D Netflix. Yeah, so just clone it in the meantime. And okay, so yeah, 6 minutes. Contract. You'll see it's like super simple for this workshop purposes. We try to keep it very simple just to showcase the ideas, but not necessarily having like a real world production grade contract or a design architecture in general. Oops. So yeah. So as you can see, and if you have experience with Cosmosm, you'd know that this looks very much like a normal contract, just like any vanilla Cosmosm contract. We have the basic entry points. We have instantiate, we have execute, we have query, and reply. Let's go over the messages just to give you guys some context about what are actually the actual flows. So first of all, the instantiate message. We're going to want to store SNP 721 code before we actually deploy this contract or instantiate this contract, and we need to provide we call it the access token, so the actual information about the code we just stored. So WASM code is basically code ID and the code hash. Now about this code hash, it's a technical thing in secret network. I don't want to go too deep on why we need it and why we use it. It's basically a way to keep interaction between contracts secure and prevent prevent the information from leaking. Okay, so every time, that's actually one of the differences between vanilla CosmWasm and CosmWasm in secret, is that we need to provide, when we call other contracts, we need to provide the code hash of this contract. And you'll see how we actually handle it in a bit. It's not complicated at all. It's fine. Entropy is not important right now, so you can just ignore it. This is a way, by the way, to create randomness. I decided not to do it in this contract, just to not overcomplicate things. But in general, this is how you do it. You, when you create a contract, you provide some sort of like initial entropy just to create the seed for this randomness. Then every time a user calls a function that needs randomness, we ask the user to provide some random entropy as well. So for the, like, it's handled mostly on the front end. You can just random, like a random string, just send it with it, and then you create like a good pseudo-random, but that's off topic. So that, like, to instantiate this access manager, we just need to provide the code for the SNP20 or the SNP721. Sorry. Now for the execute, we actually have. You can see the two basic flows we looked at earlier. So we have new video. When the video creator wants to actually list his video, you need to provide the name. We have royalty info. So if, for example, I would buy a video and then sell it in an NFT marketplace, the actual creator of this NFT will get a part of the funds. And also when a user purchases a video from the platform, the payment is also split up between this contract, or the owner of the contract, and the creator himself. So we can define royalty information. So if we go in, we can see we have like a vector of royalties, and we can specify for each royalty the recipient of the tokens and the rate, or like how much of the price goes to the creator. We can obviously, like, I haven't done it for this workshop, but we can obviously like limit the amount of royalty a creator actually sets, because technically it can set 100%, and we maybe don't want that. But okay. We also provide the URL for the cover image for the, like, when we are going to browse the catalog of the videos, we're going to see the images of the content. So that's that. And the video URL is actually a URL for the encrypted video. We have the decryption key that the creator needs to provide, and the price, where payment is an enum, and it can be, or sorry, a payment is a struct that contains a token and amount, where a token is an enum which can be either native, and then it's just a string that should contain the enum. So for example, if we list a video that we want just native secret for it, it will be just uSecret. And if we want to use SNP20s, we actually accept a struct called contract, which is an address of this contract, and the hash, as we discussed earlier. Perfect. Then when we want to purchase a video, we have two ways to do that. This message is for when we want to purchase a video that accepts native tokens. So we just send this purchase video message, and we send the tokens along with it. By the way, how many of you ever worked with CW20s in contracts? Okay, so a concept I will cover like briefly is the receiver pattern. So let's see how I can explain it. Okay, so for each contract call, we get some environment information that comes with the call, not necessarily from the user. So, for example, with every execute message, we get deps, env, and info. We're not gonna go too deep like about each one, but if we look, I think in env, no, not that, maybe info, I don't remember, sorry. Yeah, so in info, we actually, info contains like a field called funds. And funds is a list of the native tokens that this call received together with the message. So if a user sends this message like purchase a video along with, some tokens, we'll see it in funds. So if we want to access it, and we'll see it in a second, we'll do like something like info, funds, and then I get the list of the funds, the contract received in this call. For CW20s or SNP20s, in our case, it's different. It's not specific to secret contracts. It's just the way it is, because when a user sends tokens or SNP20 tokens to another contract, the user actually need to call the SNP20 contract first, right? Because I need to somehow tell the contract, hey, I'm the user, I want you to send tokens to this contract, to a different contract. So the way we do this is called the receiver pattern, and how it actually works, I don't want to spend too much time on it, but how it works is that I call a function that is called send on the SNP20 contract, and I provide an internal message. And this is the message. The internal message, what that means is that I call the SNP20 contract with all the details of like send this amount of tokens to this contract. And also, I'm providing a message that I want the SNP20 contract to call our contract with. Okay? So, receive message is an enum that contains only one message, which is purchase video. Is that clear, or should I like elaborate a little bit? Does anyone have any questions about this? Okay. So this receive message we're actually going to get from the SNP20. Like the SNP20 contract is going to call this message, not the user himself. Okay, that's an important like thing to remember. And we also have like withdraw token, which is basically the owner can just withdraw the money collected in this contract. By the way, with the receive contract, as we discussed earlier, the SNP20 to call another contract, he need to know the other contract's hash, right? Because as we said, when a contract calls another contract, you need to specify the hash for security reasons. So we actually, before that's an important like nuance, before we can accept tokens, from a specific SNP20, we need to register, like this contract needs to register his hash with the SNP20 first. We'll see it in the code. Okay. We'll get back to it in a second. So for the query messages, we can first of all query the owner of this contract. We can query like the info of a specific video, or we can just do list videos and get the information of all the videos in the contract. This is the function that our UI is going to use in order to list like and show the catalog. Other than that, that's pretty much all the important stuff. Now, for the execute entry point, let's go over new video, for example, just to showcase some of the specifics I discussed, like the hash thing and the contract calling. So when we call new video, a creator actually wants to list his video, right? So what we do in new video is we actually, so we do this thing. First of all, if the payment we are expecting is the SNP 20, we want to register our hash with this SNP 20, right? So if, for example, this SNP 20 is, I don't know, secret atom, for example. So we have this, the secret atom contract, and as I said, we want to register the access manager's hash with the secret atoms contract. So we call a function that is called register receive. And by the way, we have a library that is called the secret toolkit, which contains like a lot of helper functions with SNP 20s, SNP 721s, a lot of helpers with storage and encryption and randomness, something like CW+, if you're familiar with. So this is a secret toolkit function, and it basically, I hope you can see it, it returns a Cosmos message. So I can create a Cosmos message, and I specify like my contract's hash here. And because I call another contract right now, I need to specify this contract's hash as well. Then the SNP 20 contract, for example, the secret atom, takes my hash, stores it inside the contract, and then subsequently, when the SNP 20 is going to call this contract, the access manager is going to specify this hash. Okay? The other things are not very important. So this is the actual registration. We also store it in this contract, like we store a flag. If we registered a specific token already, more gas efficient. What else? And as you can see, we also, like at the end of the new video function, we also instantiate a new SNP 721 contract. Okay, so as we said, for each video we upload, we also want to create a SNP 721, and then after that, when the user purchases a video, he actually gets he gets minted a token of this type. So to call instantiate, it looks very much the same as in Cosmos and Vanilla. We just create, like we do response add submessage with a message with instantiate, and then we actually specify the specific message for this 721. If it's Greek to you, that's okay. Just the important part is to like get the concept. We specify like the name of the NFT, the symbol, the royalty info for like the royalty stuff on marketplaces and stuff like that. And that is all basically. Then what we do, the problem is that in order for this contract to mint new SNP 721s for each user that purchases a video, the access manager needs to know the address of the specific 721, right? To call the mint function. At this point, we obviously don't know the address of the new SNP 721 because we haven't instantiated yet at this point. So what we do is we store something we called, just a struct that's called uninitialized video. We just store it in the contract. Then we call instantiate with a reply ID. And later on, when this reply is called, like when the contract is actually instantiated, I get the contract address, I get it as a reply, and then I can take this uninitialized video and actually store, I'll show it to you. I get a contract address, and then I actually, I have the video structure, which is basically, it holds all the info about the video, including the decryption key and the contract address. And I just give the uninitialized video, and I create it from there. So we have this flow of instantiating a contract, then I get back the contract address and store it in the contract. Okay, let's now go over the purchase video flow. So as we said, we have two options to do this. We have one with native tokens and one with SNP 20. So the native token is the native token flow is a bit simpler. What we do is actually we first load all the videos we have to see that the video that the user requested actually exists. Then we try to understand what is the payment method that the video creator wants to receive. So if he just to make sure that he actually wants to receive native tokens, right? So we actually matching the we get a video from here from the video list. This video contains, if you remember, sorry. This video contains a field called info, which then contains the price, which is a payment, which can be either SNP 20 or native. So we check what's the type of the token he expects. If everything is okay, we just make sure that we receive the same denom that he expects, that we receive use secret and not some IBC token or some other native token that exists on the chain. And then we make sure we got the right amount. And at this point, we actually call a function that's called create royalty distribution, which actually what it does, it returns a list of Cosmos messages to distribute the royalties. So when a user purchases a video, he sends, for example, I don't know, 100 secret, and then we just it's pure math. It's just distributing the funds between all the royalty parties. So we create a message to transfer these tokens to each royalty member or royalty recipient. So by the end of all this flow of making sure we get the right payment method, we actually get a list of all the messages we need to send. Of course, we return errors when the payment method or the amount is not correct. And then we call purchase video implementation, which actually handles the purchase of the video, which means basically mint the NFT, right? So we call a toolkit function that actually creates a message to mint NFTs, and we just insert a mint message, which contains all the relevant data. This is a huge message because they try to we try to make it flexible for whatever use case you need. But this is SNP 721. This has nothing to do with the streaming service itself. We put the image URL, we put the video itself, the decryption key, and stuff like that. So in short, we mint the video for this specific user. Okay, so that is the flow of purchasing a video with a native token. Any questions at this point? Yeah. So it depends on you, basically. You can. I mentioned earlier that we have I have not put a limit in this contract. It makes sense to put a limit because you don't want the creator to possibly just put 100% and take it all. But there's no limit in this implementation. So it depends on you. You can when you call new video and you actually set the royalty info, you can check the royalty info and make sure it's up to a specific limit. Oh, yeah. It's unlimited, and it's limited only by the gas limit, a reasonable gas price for a transaction, basically. But sorry, but it makes sense to limit this as well as a contract, just to not get inflated gas. Yeah. Any other questions? Awesome. So this is for native, receiving native payment. Let's just see how we receive SNP 20 payment. So at this point, at the execute message match, we already. So I remind you guys, the actual caller of this function is the SNP 20 token. He calls receive with all the relevant information. And we already extract the inner message that the user sent originally, which is purchase video. It's the only message that this contract supports. We get a video ID, and then we call purchase video SNP 20, which is a different function. And the implementation of the purchasing of the video is the same with both native and SNP 20s. We just mint a token, right? So it doesn't matter what payment did I get. Just the difference is just the parsing of the payment method and the handling of the denom and stuff like that. So again, we get the list of videos. We make sure we actually get the right payment method, which is a SNP 20. We extract the actual contract that the user expects to receive the payment by. We make sure that the sender of this message is the payment method address, right? Because the user says, I want to receive secret atom from this address. Now we need to make sure that secret atom is the actual contract that called this contract. So we make sure the address is the same. Then, I checked earlier that the amount actually checks out. And once I know the payment method is valid, I create call royalty distribution again, which we don't need to go over again. Then I call purchase video impl again, which creates the mint message. And we also pass along the royalty messages. So that's for purchasing a video with SNP 20. As I said, it's very similar, but it's a little difference from the native method. Any questions about that? Cool. So that's basically it for the contract, like the important stuff. I'll just show you like another quick thing. Let's say a user queries a video info, right? Now, the easiest thing to do is just load the list of videos, find the specific video the user like queries about, and then, oh, what's that? Sorry, it does that sometimes. Yep. The easiest thing for me is just to return this struct, right? Because that's what I get from the storage. Do you guys maybe can guess why I can't just return this structure? Like, what's the problem with just get the list of videos and just returning it? Yeah. Might be, but let's say it is serializable. You have any other idea? Maybe something privacy related? So the problem, I mean, when we store the video information in the contract, we also store the decryption key. Now the video query at this point is permissionless, because when the user actually wants to get the decryption key, he holds an NFT. He queries the NFT. This contract has nothing to do about with regards to giving the user the decryption key. So all the queries are permissionless. But what I'm trying to showcase is that sometimes, like, we need to be very careful to not by mistake leak information we don't want to. So in this case, we have the decryption key in the video structure, and we don't want to by mistake just show it with a permissionless query, because then it beats the purpose of all of this. Yeah. When the buyer received the NFT holds the decryption key in the private metadata. Only the buyer or the owner of this NFT can access the private data. So by the time you own this NFT, you have access to the decryption key, but you don't want to show this decryption key with a permissionless query, because then no one will have to buy the NFT in order to get it. You can share it, yeah, with this implementation. I'm not sure if you've been here from the beginning. Have you? Yeah, okay. No, that's perfectly fine. We discussed it earlier that it's a very simplified and basic implementation. It's for sure can be improved. It's just to showcase the possibilities with content monetization. So is that answers your question? So the network, the infrastructure works like that. We have secure enclaves. All the decryption and encryption keys are stored in an enclave. This is something we built with a contract on top of the network. So you can definitely implement it with secure enclaves and design something more production grade. But this is a simplified version for this workshop purposes. Okay. Answers your okay. Yeah, so what I was saying is just to explain the concept is when we actually implement this query, we actually return, we build an object from type public video. So I created a new type that contains only the relevant public information that I want to share, and not the decryption keys, because the decryption keys the user will get when he purchases the SNP 721. Cool. Okay, so that's the smart contract side of this application. Now we have everything to do with the front end and the UI. Let's back to the presentation real quick. And I want to explain you guys like how we tackled the problem of having an encrypted video uploaded to like a IPFS or a file service or something. The problem is obviously that video files get very large, and the act of downloading a few gigs of video, then decrypting the whole thing and showing it to the user is very it's gonna take a long time. It's a very heavy thing to do, and obviously streaming services don't do this. They have some kind of method to, while the files are encrypted, they still stream it and decrypt it on the fly. Okay, so how they actually do it? They have obviously super complex ways, like production grade ways to do it. For our use case, we used a pretty simple way. There's actually a format called M3U8, which when we transcode a video to this format, it actually breaks the video to chunks. So you see on the left picture there, we have several parts. This is just a 1 minute video, and we have like like a 30, I think, or 20 different parts that it breaks into small size. And every part is encrypted by itself. So when the player actually receives, he reads the M3U8 format. This is the right image, is how this format actually looks like. And it's like a metadata. It explains like how what are the names of the files and the encryption methods and all that. So as you can see, there's a line where I marked the red square that actually specifies the encryption method, which is AES-128 for this purpose. And then the format accepts to receive a URL for the encryption or the decryption key. And the problem, like it's not really a problem, it's a bit annoying because we don't actually hold the key anywhere. It's on chain. We don't have a URL for it, right? The video player component can't just query the decryption key because it's in the NFT and the user holds it. So we did a little trick, a little hack to overcome this. We put the URI as you see here, just like key//0.key. Then on the UI, sorry, we look for that string and replace it with something else. By this point, we can, like the UI queries for the user for his decryption key. Then we have something called an echo server. What an echo server does, super simple. You can see it later. You have this on the repo you cloned. It's super simple. It just receives a post message and returns it. Like it just returns like the same. So if we send a request to the echo server with the decryption key, let's say 1234, the echo server gets this parameter and then just returns it. Okay. We do this just so we have an actual URL because for some reason we weren't able to put like anything else. It really maybe it's a problem with the video player like the video component we worked with, but it actually expected a real URL or a real server to return the key. So it's just a little trick. We don't have to spend too much time on it. But is there any questions about this? Okay. So yeah, so this is how it looks like. After we transcode and encrypt the video, we receive all of these files. So as we said, we have the M3U8, which is like a metadata file, and we have the actual chunks. We upload all of this to IPFS. All of this needs to be in the same the same path, because the player expects all the other files to be in a same relative path. So we need to upload all of these to the same location. And then we handle the decryption on the UI. So, again, is there any questions? Are there any questions? Yeah. So the size of the files. Oh, I see what you mean. I actually don't remember how what's the difference was with an actual large video we did. No, we actually did like a real we did an NFT drop with Kevin Smith. Never mind, not like it's off topic, but we did an actual like he distributed his movie exclusively with NFTs with this type of encryption. So I don't remember like the actual differences with real world videos, but for this case, I have it here somewhere. Oh no, actually I have it in another place. I can look it up later. It's a bit bigger than the actual video itself, but it doesn't really matter that much because it splits into chunks, small chunks, and it works. Any other questions? Cool. So what I want to do now, I don't want to spend too much time on the front-end side because I mean the front-end is a bit more easier and I think like it's less interesting. But you can definitely go over the front-end implementation after the workshop is done. What I want you guys to do, and like because each of you have like a different type of architecture and laptop, and we have Mac and Linux and all that, so it can be kind of difficult for all of you guys to actually configure your environment properly for everything to work smoothly, and we don't have a lot of time. So instead, in the dNetflix repo, you have this button called Open in Gitpod, and that actually, I don't know if you're familiar with Gitpod, but it actually creates a virtual environment for you based on Docker, and it like opens it in a VS Code, and we can work from there just to simplify things. So if you want to follow along, what I'm going to do now is compile the contract, spin up its, when you open the Gitpod, it spins up like a local node of secret that we can work with. And I'm gonna compile the contract, I'm gonna upload it and deploy it to the node, and we'll see how we do the UI stuff. Okay, so if you want to follow along, just go to the repo and click on Open in Gitpod and follow along with me. It's a bit small, right? A bit too small. Is this okay? Can you see the text? Okay. So once you open Gitpod, you can actually see we already have a node running. And by the way, we also have like this specific workspace clones the repo itself of the workshop and all that. But we also have a clean version of like just a Gitpod environment that just spins up a node, and you can interact with it externally. So in order to compile the contract, we need to run make, and the make command, the make rule is access manager compile optimized. It's going to compile the contract and then just compress it for the file to be smaller. So it's going to take a minute. While it compiles, if you want to follow along, I'd ask you to open the actual repo locally as well, and just run npm install in the main path of the repo, because we're going to spin up the front end locally, and it will talk to the remote node on the Git pod. While we're doing this, we can also go to mobile video, which is where the actual front end site files are, and we're going to want to go to mobile video env. And if you don't have the env file, you can just copy the env.example and call it .env. That's important, like the name. And then you will want to configure it as follows. I think most of it will be filled out. We will in a second, when we deploy the contracts, we will fill out the actual address and hash. But what we want to do now is to fill out the URLs for the node. So what we do is we just copy the URL of the Gitpod environment, copy it, and then we're going to paste it for each of these endpoints. And for REST, we're going to do the way Gitpod works is that you can specify the port in the first part of the URL. So you can do 1317 dash, and that's going to go to the 1317 port in Gitpod. So we just need to configure it right now. So just paste the URL in each of these endpoints, and for REST URL you want to do 1317. For RPC you want to do 26657. And for gRPC web, you want to do 9091 or 1991. Then these two environment variables you want to keep as is. I think it's the same in the example. Or, sorry. Yeah, you can just keep it the same. And these two, I have previously filled them out. We'll fill it in a second. So in the meantime, I got the contract compiled and good to go. I actually have like helper scripts to help with the like deployments of stuff. So first, we'd want to run npm install in here too. It installs secret.js, which is the JavaScript library to interact with secret, which you can use in front end or in scripts or like backend scripts. The first one we want to run is node snip 721 scripts store. What it's going? Oops, what's that? It can't work in the first time, right? Oh, that's because I didn't copy the env file. So I will just copy the env.example. I will rename to env, and then I will just keep the parameters as is, because the node in here runs locally. And I will run the script again. Cool. And so if you remember, we need to store the SNP 721 code first, then we need to specify the code when we instantiate the access manager. So what we want to do now is to actually specify these parameters in the end file so the other scripts will work properly. So we, code ID is 1, code hash will copy here. And we haven't deployed the access manager yet, so it stays empty for now. Yeah. Oh, it's super small, right? I'm sorry. Before that, I did npm install, just to install secret.js, and then I copied. You see here, I copied the env.example, and I created a .env file, and we actually need, like, it reads this specific file name. So we need to copy it and just run the script. So now we want to actually deploy the access manager. So we compiled it. We have two files here. One of them is .wasm, one is .wasm.gz. They're the same, it's just compressed. So the file size is smaller. And we want to call deploy. So it's a node access manager scripts deploy. And if you want to experiment a little bit with secret.js, you can just open the scripts folders and see like the actual scripts. They're pretty simple and very intuitive. So we call deploy.js. What it does is stores the contract and then instantiates it with a default message. So as you see, it stored the code ID, and we have our access manager address. Now we want to take this address and specify it for the front end to use. So we go to the front end and we paste the contract address here. So this environment variable expects to get the access manager address. And now we need to specify the hash. In order to get the hash, I need to do a simple CLI command. So I do, and I can get it with secret.js as well. So I do, but it's better to do it offline and not like while the front end is running, just to like for efficiency. So we do secret CLI queue compute. On most, by the way, on most chains with the CLI, the COSM was a module called WASM. For us, it's compute. So we do secret CLI queue compute contract hash and paste. The gitpod things kind of ruins the you can see it very well, but the command is secret CLI queue compute contract dash hash and the contract address. Okay, so it's this. I'll just write it here. Okay, that's the actual command. I'll erase this. And now that the access manager is deployed, I can actually oh, sorry, I forgot. We need to actually put the hash in the end file. So I'll run the query again. I take the hash, paste it here. That's not important, yeah. And we also, wait, yep. We also want to remove the leading 0x. Otherwise it won't work. Now we have all the configuration for the UI, and we can run it. So we go to mobile video folder. I think we need to run npm install one more time. Let's wait for it to finish. Cool. We ignore all the vulnerabilities elegantly. And now we run npm run dev. It spins up the UI, the front end. And then it shows like the URL we can click to access it. You might get like a message saying like a problem with it's a self-signed certificate. Doesn't matter, just click continue. And this happens right now because I actually probably have the previous container I worked with is configured in Kepler, so I'll just remove it. And I'll do a hard reload. Oops. Okay. Oops. Now that's the actually thing I need to get, which is this Kepler pop-up. I just approved to use a specific chain ID. I approve it and approve connection to this site. And this is our UI. Very basic right now. Once we have some videos, I will actually be able to see them here. Just for fun, if like we can also list a new video through the scripts. So for example, we can call node access manager scripts new video, and it creates a, and of course it doesn't work. Oh, for the script to work, I need to put the actual access manager address here as well in the env file. So I'll copy it from here. Then run new video.js. And it just lists a new video with pre-configured parameters. So just so you see, this is how the code looks like. We call execute contract with a specific message. And as you can see, I already pre-uploaded the videos to IPFS just in order to save some time, but you can do it as well after. We have the decryption key and we have the price. We set it to use secret with I think 1 secret, or no, 10 secret. So yeah, that's how it looks like. And now in the UI, if I refresh, I should be able to see this video. Now we actually create the UI creates this creates a permit for us. So this is what it looks like. We actually get a Kepler window, and we get a Kepler window because you obviously, I barely see it, so you obviously can't. But if we zoom in a little bit, we can see that how the permit data actually looks like. So it looks like this. We have type query permit. The value is permit name. We have permit name here because if we choose to share this permit like after that with some other party, we can actually revoke a specific permit. So if I want just to temporarily give access to someone, and then I want for them to not have access anymore, I can actually like specify a permit name and revoke it. It won't work anymore. Okay, so that's an important functionality. Then we have allowed tokens. So what tokens is this permit good for? And the actual permissions that this permit allows. So technically we can create a permission that is only like, I don't know, if we talk about NFTs, we can have a permit that only allows the holder of a permit to view only the balance, or only the amount of tokens that I have, or only access to a specific token. Okay? So here we have two permissions. We have one balance, one owner. Doesn't really matter like what it actually means in this case. So in short, as I mentioned before, this is a message that my private key, I need to actually sign this message in order for the contract to validate it and allow access. So I need to click on approve, and we sign this permit here because, as you see, we have one video and we want to just to check if the user already have, like, is he already purchased this video or no. So we actually check the balance of this SNP 721. We approve it, and the video loads. Hopefully, like, it's a public IPFS endpoint, so some things might take some time. Yeah, the cover will load eventually. We can click buy. Now we send a transaction, right? With purchase video, with the video ID, and with actual, like we actually, it's a native, it's a native payment method. So we actually send some funds. Here we have the video itself. By the way, any of you know this video? Yeah? Yeah, okay. It's like an open source something, right? It's like the only video you can you can use on a. Oh yeah. Oh, cool, cool, awesome. I actually, like, we always work with, we took this video and we cropped 1 minute of it, so I only know the first minute. I always like I'm like, I want to watch the rest, but I never got a chance to. All right, so we send a purchase video transaction, and in a few seconds, it loads up again, and now I can actually play this video. Okay, so cross fingers. Let's see if it works. Come on, IPFS endpoint. It decrypts it on the fly. So it streams the chunks bit by bit, and every chunk is decrypted individually. It's gonna take some time, but what we can, like, at least we see that it knows it's only 1 minute, and it's gonna load at some point. Yeah, so in this UI, you can actually also like list a new video. It comes with a preloaded values with the pre-uploaded movie, the 1 minute part. So just you can play around with, and this is the actual decryption key, and you can set the price. We only worked with native tokens here, just for simplicity, but you can play around with it if you want. You can play around with the royalty. And let's see if it loads. Still no, I'm sorry. But one last thing I want to show you guys, and I'm not sure you'll be able to follow along, just because I will show you how I transcode the actual video, which is an important part, right? So the reason you might not be able to follow along is that I use a tool called FFmpeg. It's kind of hard to configure. Personally, to be honest, I haven't able to run it on Mac. It's possible for sure, but like you can configure it somehow for sure, but I wasn't able to. So just for simplicity, I will show you guys how I do it. So we actually have, like, for all this flow of encrypting, encrypting a video and showing it on a UI, we have a like an example repo that's showcasing it. So if you go to GitHub, you go to mobile video example in this repo. You can clone it later, but we have a video transcoder script here. So let me just open it up locally. Okay. Oops. Yeah. I know what? Handbrake? Oh, is it? Huh. I put a note to myself, if you don't mind. I'll check it out. Handbrake? Thank you for that. I'll check it out at some point. So yeah, so we opened the video transcoder folder. You see we already have an example transcoded video here, but I think we can just delete it. Okay. Okay, so now I have the actual video here in the MP4. Let's see if it loaded up already. Still no. Okay, we'll come back to it. In the repo, you have all the README files that actually explains like how to run these things. We wrote a script to make the transcoding part easier. So we need to run no transcode input directory, which is like you can encrypt several videos at a time. So we need to put an input directory, then output directory. So, for example, we have the video here, the MP4. I very hope we'll get to actually see it, because I want to share with you guys my experience from that first minute for you to, maybe we'll do a shared screening with the full video. So we go to video transcoder and we run node transcode input directory, which is relative, so TMP, and output directory, which is in this case encrypted vid. And because I have an NVIDIA GPU, I can actually specify to use NVIDIA just to make the transcoding faster. So I'll do that. It's doing its thing. It might take a while for a large video. And now we're finished. And we have the output in the output directory. We have all the files here that we saw in the presentation. We have the M3 UI. By the way, the transcoding script also randomizes an encryption key for you, just for example purposes. You can change it. You can do whatever you like. You can take parts of the scripts and play around with it. So we can see the M3 U8 format with all the parts. Whoops. We can see the placeholder string that you saw in the presentation. We put that as well as part of the script, and we also get a file called output list, which is just a CSV of the name of the video and the actual decryption key. So now we're kind of out of time, so I don't want to spend any more of your time, and I'm getting kind of hungry. But we can take all of this directory or this entire folder, we upload it to IPFS, and then we can use this decryption key, and we can actually where is it? We can put like the actual data here. You can upload an image if you want. We put the. You see, we need to put the M3U8 path, and all the TS, the chunks, need to be on the same path, as I mentioned earlier. We put it in the video URL. We put the decryption key, and that's basically it. Let's see one last time if we can load that video. Come on. Oh, sorry. The reason it doesn't work is because I forgot to activate the echo server. You remember? So we don't actually get any encryption key. Sorry for that. So I go back to the workshop repo. I open another terminal. I go to echo server and just node index.js. And you can see, nope, not this. You can see that this is a very basic server. It just gets the encryption key and returns it. Now that it's up, we should see a video playing, hopefully. Come on. Yeah. It's like that sometimes with IPFS. Okay, let's give it a minute. Speaking about IPFS problems, I want to spend really 2-3 minutes just to talk about how do we actually take this to production. So it's obviously a demonstration, and it's obviously it's not perfect. It's not ready for production as is. For example, for this problem, what we did to face it, and we still keep the same all the principles of this centralized streaming service when we do this, is that we took the IPFS files and we actually cache it in a centralized server of ours. So it's still available in IPFS, always for users to use if they want. If we disappear tomorrow, it's still there, it's still available. But if we actually, oh, there we go, yes. If we actually want to provide good experience for users, we sadly can't rely on IPFS currently because it's very slow, especially for large movies. So we just cache it on a dedicated server, and we can do the same thing. We can just provide the file that we cached instead of going to IPFS, and it just works the same way. We hold only the decrypted files, so nothing everything still the same principles apply here. Obviously, the decryption key thing that users can just share it is a problem that we can it's possible to solve it with more complex design. We can work with I think he left already, but he mentioned we can work with secure enclaves to do this. If we do everything on chain, including we can actually spin up a chain dedicated for this, then everything stays in the same chain. Then we actually don't have to expose the decryption key to the user, because he has to work against the actual contract, which is a very, very good idea. I think I don't remember who mentioned it, but so yeah, there are some things we can take. We need to steps we need to make in order to take this to production. But the purpose of this workshop is just to showcase what's possible with privacy on chain. What cool stuff. As we see, we have a fully decentralized system, fully on chain. We have nothing off chain here. We don't rely on anything, not for randomness, not for privacy, not for storage, which is very exciting for me personally. And we all control stays with the user, and we don't rely at all on any other centralized party. I see we loaded just a couple of seconds, but we have a video playing, which is good. Buffering, yeah, we got 3 seconds. All right, that was it. Thank you all for coming. I hope this was, yeah, thank you. I lost the word. Thank you, guys.